Hi everyone, welcome back to Calculus 2 by example. We're still in the review section. This next problem we're going to look at involves Riemann sums. So this is what we want to do. We want to find the area between a function f of x equals x minus x cubed in the x-axis on the interval from 0 to 1. So we're going to do this by approximating it. So here are our axes, here's our function. And because the function is curved, we don't necessarily have, maybe we don't have a good way to find that area. So what we do is we approximate the area underneath that curve and above the axis by using a lot of little rectangles, okay? And then we add up the areas of those rectangles, okay? So each rectangle has width, we call delta x, so delta x stands for the change in x. So the width of each little rectangle is delta x. And then we find the height of the rectangle by plugging a value into the function. So the function tells us the height of the rectangle. And delta x is the width of the rectangle. And if we multiply the width by the height, that gives us the area of that rectangle. And then this sigma, this capital Greek sigma, means summation. And so that means we're adding up each of those little rectangles, okay? So we want to add up each of those little rectangles, and that will give us an approximation of the area under the curve. Now, if I have more rectangles, if I increase the number of rectangles, then I get a better approximation. And this brings us back to what I discussed in the first video in this series, which is that in calculus, frequently we'll have a problem that we don't have an immediate answer for. And so the way we tackle that problem, the way we try and solve that problem, is by first approximating the answer using something we can do, but we want to approximate it in a way that we can refine it. So in this instance, we're approximating the answer by using the rectangles because I know how to find the area of rectangles and I know how to add, okay? So I find the areas of these rectangles and I add those together, and then I look at what happens to the refinements as I increase the number of rectangles, and that's where this idea of taking a limit comes in. So I'm going to take the limit as n approaches infinity, where n is the number of rectangles. So we're going to have more and more and more rectangles, and as we take the limit of the number of rectangles as n goes to infinity, and really here I want the width of the rectangles to all go to 0. So the widths are going to 0 and the number of rectangles is going to infinity. That will give me the exact area under the curve. At that point, this summation goes from a summation to an integral. And we go from an approximate area to an exact area underneath the curve. The integral symbol is in fact an elongated S. It's a notation that Leibniz developed in the 17th century. And it stands for summation, and it's this idea that we're summing up infinitely many rectangles that are all infinitely narrow. Okay, so they're infinitesimally wide. They have a width that you could sort of think of as not 0, but smaller than any number you can name. Okay, so this summation turns into an integral when we take the limit. So the rectangles become the exact area underneath the curve by taking this limit, by using this refining process. Okay. We evaluate this rectangle or this integral by finding an antiderivative. The antiderivative of x is 1/2 x squared, of x cubed is 1/4 x to the 4th. Our limits of integration are 0 to 1. So we plug in the 1 and we get a 1/2 minus 1/4. We plug in 0 and get a 0. And so when we're done, we get the area underneath the curve is 1/4. Okay. So Riemann sums, these summations give us an approximation of the area. And if we take the limit as the width of the rectangles goes to 0 and the number of rectangles goes to infinity, that summation becomes our definite integral. And that definite integral in this example gives us the exact area underneath the curve. Again, I want to emphasize this idea that in calculus, when we want to solve a problem and we don't know how to, we start by finding an approximate solution. but we always want to find that approximate solution in a way that we can consistently refine so that we can take a limit and find an exact solution. Okay, so that's it for this portion of this sequence of videos. In the next one, we're going to talk about finding integrals by first looking at derivatives.